Hello, today I will be doing a solubility presentation. Um, we'll be working through a problem on solvents dissolving solutes. So the problem will be to select the solvent that would best dissolve the solute. We're giving two possible solutes, boron trifluoride and nitrogen trihydride or ammonia, and two possible solvents for them, and the option of both of them being good solvents or neither of them being good solvents. So the two solvents given for boron trifluoride are H2O, water, and carbon tetrachloride. The two solvents given for ammonia are water again and hexane, or C6H14. Information that we need to know before we can solve this problem is the molecular shape of these molecules and the intermolecular forces acting on them. So it's important to know this because of the principle that like dissolves like. So similar molecular shapes or the ways that a molecule is made up can affect the intermolecular forces that the molecule experiences, and this in turn makes the molecules either polar or nonpolar. And polar molecules are also best at dissolving other polar molecules, so a polar solvent will best dissolve a polar solute, while a nonpolar solvent will best dissolve a nonpolar solute. There are different molecular shapes possible, like linear, trigonal, planar, and tetrahedral. Those are the basic shapes. The shape of a molecule depends on the molecule's bonded atoms. So if a molecule has equal bonds, then it's not likely to experience a lot of force outward or dipole moments that are strong. But it's also important to know whether or not a molecule has lone pairs, because these can change the shape that the molecule takes, and also whether or not a molecule will become polar and experience dipole moments. Shown here are also the shapes of the molecules that we were given, and now I will explain their shapes and their properties. So boron trifluoride has 3 fluorine atoms attached to a boron atom. So boron only has 3 valence electrons, and you can see here that it's got 3 bonds to fluorine, so it has no lone pairs left. And since the shape here is given and it is trigonal planar with 120-degree angles between the bonds, you can see that the bonds that F's to B have are on opposite sides. It forms a bit of a triangle shape, and the force that the fluorines exert outwards, like pulling electrons towards themselves and away from the boron, are in opposite directions, and this kind of cancels out, making this molecule nonpolar, which means that it is not capable of hydrogen bonding. The next molecule will be ammonia. This molecule is tetrahedral in shape. It has 3 bonds to hydrogens and 1 lone pair on the nitrogen. This means that the nitrogen is more electronegative than the hydrogens, and so it's pulling electrons towards itself, and this makes the whole molecule polar because it experiences dipole moments. And since it experiences this, then the polar molecule is also capable of hydrogen bonding because of the lone pair on the nitrogen and the hydrogens that are present that are slightly more positively charged and the nitrogen slightly more negatively charged. Water, or H2O, is a good solvent. It has 2 hydrogen bonds and 1 oxygen. The oxygen has 2 lone pairs. This is because oxygen in the periodic table of elements, if you look at it, and its group, it has 6 valence electrons. 2 of them are in the bonds to hydrogen here, and then the rest are in the lone pairs. This gives it a bent linear shape, or otherwise a tetrahedral shape, because the lone pairs also act as pseudobonds. And since the lone pairs are present on the oxygen, that means that the oxygen is slightly more electronegative and the hydrogens are positive. So there's dipole moments experienced, which make this a polar molecule. And since there's also lone pairs on the oxygen and there's hydrogens in this molecule is capable of hydrogen bonding to other molecules. Carbon tetrachloride is the next molecule that we have to go over. Carbon tetrachloride has one carbon central atom and 4 chlorine atoms. These chlorine atoms are bonded on opposite sides of the carbon. Carbon itself has 4 valence electrons, and here they're all bonded to a chlorine atom, which leaves it with no lone pairs. Here we see that it has a tetrahedral shape, and since the force of the chlorine atoms is pulling electrons outward, but they're on opposite sides, this kind of cancels out the force and makes it a nonpolar molecule, and also makes it incapable of hydrogen bonding. C6H14, or hexane, has 6 carbon atoms and 14 hydrogen atoms. Here we can see the central carbon atoms each have 4 bonds, and they're either bonded to a hydrogen atom or a carbon atom. There's not a large electronegativity difference between carbons and hydrogens, so this molecule doesn't experience large dipole moments. Even though the carbons are bonded to different molecules, it's not a big difference, so it doesn't make it polar, since it experiences no extreme pull of electrons towards one side of the molecule or the other. So since it's a nonpolar molecule, it is not capable of hydrogen bonding. So now we can go back to the problem. Select the solvent that would best dissolve the solutes. The two solutes given are BF3, boron trifluoride, and NH3, ammonia. The possible solvents are water, carbon tetrachloride, and hexane. So we went over their molecular shapes and whether or not these molecules were polar because of their intermolecular forces, and we saw that boron trifluoride was not polar, while ammonia was polar because of the lone pairs on the nitrogen. Water was also polar because of the lone pairs on the oxygen. Carbon tetrachloride was not polar because it experienced opposite poles that canceled each other, same as boron trifluoride, and hexane is simply nonpolar. All of these molecules experience London dispersion forces, but that's the weakest force, so we have to go with the strongest force to see whether or not they're polar, and we saw that only 2 of them were polar, ammonia and water. So for the first problem, the solute boron trifluoride is dissolved by a nonpolar solvent, since this molecule has forces that cancel each other with the fluorine atoms, and so its possible solvent is carbon tetrachloride. Ammonia has lone pair on the nitrogen, and it has hydrogen atoms, which means that it is capable of hydrogen bonding and is a polar molecule. Hydrogens on the water molecule and the lone pairs on the water molecule also make it capable of hydrogen bonding, and it is a polar molecule. So the solvent for ammonia will be water.